We're back again. This is part 3 of chapter 26, still dealing with refraction as well as Snell's law. This topic deals with the concept of internal reflection. I'll describe what that means. I show here an interface between water below and air above, and there is an incident ray originating in the water. It's bent as it passes into the air. We have then the incident ray and the refracted ray. The angle of incidence is 40 degrees, and a Snell's law calculation will show you that theta 2, the angle of refraction, is 59 degrees. These are the angles that are measured with respect to the normal line. A line is perpendicular to the interface. Perpendicular. What I show in this diagram, in addition to the incident and refracted rays, is the reflected ray. The interface acts like a mirror, not a very efficient one, however, but it nevertheless does reflect light that is incident on it from below. I indicate that the percentage of the energy carried by the light wave that passes into the air, in this case, is 70%, while the remaining 30% is the reflected energy. To calculate the angle of refraction here, as I pointed out, you use Snell's law. We'll do the same thing with a different angle of incidence, higher than the 40 degrees, and look to see what happens. So let the angle of incidence from water be 46 degrees. As before, there's a reflected ray that follows the reflection law, 46 and 46, just as was the case back here. The angle of reflection, same as the angle of incidence, 40 and 40. In this case, one could calculate that the angle of refraction is 73 degrees. And in this case, only 20% of the light energy that begins in water makes it out into the air. The remaining 80% is the reflected ray energy. Now we ask the question, what would have to be the angle of incidence in order that zero light energy gets out into the air and 100% of it is reflected back downward? We call this total, or 100% internal reflection. What is that special angle of incidence that would cause all of the light energy to be reflected back into the water? Well, we give a special name to that special angle, and it's called the critical angle for 100% or total internal reflection. And subscript C on the theta means critical. What is a critical angle in the case of the water-air interface? Well, Snell's law has us a 1.33 for the water below times the sine of the unknown theta 1 equals 1.00 for the index in air above times the sine of 90 degrees. When theta is, the angle of refraction is 90 degrees, zero energy escapes into the air. All of it goes downstairs. And what angle theta 1 will cause this equation to be true? There's your answer. This is called the critical angle for total internal reflection for the water-air interface.